Scientists superheat solid gold to 14 times its melting point, bypassing theoretical limit. Scientists just blasted solid gold to a staggering 14 times its melting point, and it didn't melt. Sounds impossible, right? Gold normally liquefies at a relatively modest 1,064 degrees Celsius, 1,947 degrees Fahrenheit. Yet for a fleeting instant, researchers watched a wafer-thin gold from shrug off temperatures above 14,000 degrees Celsius and stay perfectly solid. But here's where it gets controversial. By doing so, the team appears to have leapfrogged a long-standing theoretical wall called the entropy catastrophe. Before we dive into the laser flashes and mind-bending numbers, let's unpack that intimidating phrase in plain English. Entropy is a measure of disorder. Picture the difference between meat ice cubes and splashy liquid water. Physical laws say that in a closed system, entropy can only go up over time. When a solid turns into a liquid, its atoms jiggle around more chaotically, pushing entropy higher. Physicists predicted that if you somehow heated a solid far past its melting point, its internal disorder would eventually catch up to that of the liquid state. That tipping point, roughly 3 times the melting temperature, was dubbed the entropy catastrophe. For gold, theory places it near 3,200 degrees Celsius. Go any hotter, the argument went, and the crystal lattice could no longer survive. And this is the part most people miss. Actually reaching that limit isn't just a matter of cranking up the heat. In practice, a whole hierarchy of catastrophes usually sabotages you first. Microscopic cracks, surface defects, or plain old thermal expansion turn a solid into a liquid well before you can test the high entropy frontier. It's like trying to break the sound barrier in a car that falls apart at 50 miles per hour. Thomas White and colleagues at the University of Nevada, Reno decided to sidestep those roadblocks with raw speed. They took gold films only 50 nanometers thick, about half the size of a typical virus, and hammered them with an ultra-bright X-ray laser pulse lasting 45 femtoseconds. 1 femtosecond is a millionth billionth of a second. Blink, and about 30 quadrillion of them pass. Think of a metal as positive ion cores swimming in a free-roaming ocean of electrons. The laser's X-ray photons smack those loose electrons first, dumping energy into the electronic sea. Almost immediately, that energy spreads to the atomic lattice, hiking up the atom's average kinetic energy, what we humans perceive as temperature. Because the heating was essentially instantaneous, the lattice didn't have enough time to expand, crack, or otherwise create weaknesses that lead to superheating gold beyond the entropy catastrophe limit, breaking physics boundaries. Have you ever wondered what happens when you push a material to its absolute limits? We're talking about superheating gold, a metal so precious that even its extreme transformations are fascinating. But here's where it gets controversial. Researchers have now superheated gold beyond what was previously thought possible, reaching temperatures that defy traditional thermodynamics. And this is the part most people miss. It's not just about the heat, but how fast you heat it. Using ultra-short laser pulses, scientists have bypassed the so-called entropy catastrophe, a theoretical limit that said gold couldn't go any hotter without turning to liquid. But here's the kicker. They've shown that gold can indeed be superheated to 14 times its melting point, without losing its solid structure. How did they do it? By measuring the ion temperatures directly, using a pioneering technique called inelastic X-ray scattering. This method allowed them to bypass the complexities of electron-phonon interactions and measure the ion velocities directly. But the implications are far-reaching. This discovery challenges our fundamental understanding of how solids behave under extreme conditions. It raises questions about the ultimate stability limit for superheating and whether there's even an upper bound. Could this be a game changer for materials science, opening up new possibilities for high pressure and high energy density research? The debate is just beginning. What do you think? Could this be a breakthrough that rewrites the rules of thermodynamics? Or are we missing something crucial in our understanding? Share your thoughts in the comments below. Gold superheated to 19,000 K, defies physics entropy catastrophe, groundbreaking SLAC discovery. Imagine gold defying the laws of physics. A groundbreaking study has shattered decades-old theories, redefining our grasp of superheating. Measuring the temperature of extremely hot materials has always been a formidable challenge. Whether it's the fiery plasma of the sun, the intense core of planets, or the extreme conditions within a fusion reactor, these warm, dense matter states can soar to hundreds of thousands of degrees Kelvin. Accurate temperature readings are vital for understanding these complex systems, yet they've remained elusive until now. We've mastered density and pressure measurements, but temperature has always been a guessing game with massive uncertainties, hindering our theoretical progress, explained Bob Nagler, a scientist at SLAC National Accelerator Laboratory. This long-standing issue has finally met its match. In a pioneering study published in Nature, researchers have, for the first time, directly measured the temperature of atoms in warm, dense matter. Unlike previous methods reliant on intricate and unverifiable models, this novel approach directly tracks atomic speeds, thereby determining the system's temperature. This breakthrough is already reshaping our world. The team managed to superheat solid gold far beyond its theoretical limit, defying 4 decades of established physics. Nagler, along with Tom White from the University of Nevada, Reno, led this collaborative effort involving institutions like Queen's University Belfast, European XFEL, Columbia University, and more. For nearly a decade, they've tackled the challenges of measuring extreme temperatures, particularly the fleeting nature of these conditions in the lab and the calibration complexities. We've finally achieved an unambiguous direct measurement, offering a method applicable across the field, Light remarked. Under extreme conditions, materials can enter exotic phases with unique properties. At SLAC, researchers are delving into some of the most extreme forms of matter ever created. Using SLAC's MEC instrument, the team superheated a gold sample with a laser. As the heat surged through the sample, atoms vibrated at speeds corresponding to their rising temperature. Ultra-bright X-rays from the LCLS then passed through the sample, scattering off the vibrating atoms and revealing their speed, and thus their temperature. This innovative technique showcases LCLS's leading role in laser-heated matter research, said Sigrid Glunzer, a co-author and director at SLAC. LCLS, combined with these methods, is pivotal for advancing high-energy density science and applications like inertial fusion. The team's excitement grew when they uncovered something unexpected: the super